In this video, we're going to talk about continuous random variables, a distribution of continuous random variables, and how to think about probabilities within them. A continuous random variable x takes all the values in an interval of numbers. So instead of talking about single events with continuous, we talk about intervals of events. Because a probability of a single event, let's say x is equal to some number k, is actually 0 for a continuous random variable distribution. The probability distribution of x is described by a density curve. The probability of an event is the area under the density curve and above the values of x that make up the event. So area is going to be equal to probability. Larger the area, larger the probability. So an example of a density curve is given to the right. This is what's called a uniform density curve. All of the values have the same probability in terms of the height. This is a 1 by 1 rectangle, so the total area is 1 times 1, or 1, which makes sense because it has to be 100%. The shaded region, if you find that area, it is 0.4 as the base and 1 as the height, in case you're confused about that. That's 0.7 to the right and 0.3 to the left. The difference between the two is 0.4, which is the base, and the height is 1. The area is 0.4, which makes the probability from 0.3 to 0.7 equal to 40%. So the area of this rectangle is 0.4, so that means the probability of this interval of events, 0.3 to 0.7, is 40%. Now for a uniform distribution, a rectangle is a very simple shape to find the area of. If you were to look at a normal distribution, this bell-shaped curve is very difficult to find the area of. For this, this example here, it looks like a trapezoid almost, but this is not a linear or a line segment. This is actually a curve here. So finding the area using our geometric formulas doesn't really work. So when it's normally distributed, you actually can use table A, just like we did in chapter 3 in finding proportions of values. So in this case, we have a mean of 64, a standard deviation of 2.7, and in between the values 68 and 70, that's height in inches, they want to find the probability of finding that interval or getting that interval. So what you need to do is convert both of these to z-scores and then use table A to find the proportions under the curve. So first, we'll do z of the 68. So 68 minus 64, the mean, divided by the standard deviation, 2.7, and you get 1.48. And when you look at table A, the proportion of data to the left of this z-score is 0.9306. If you do the z-score for 70, you get 70 minus 64 divided by 2.7. And when you do that, you get 2.22, which is 0.9868. Now these two numbers are both very large, but what you don't forget that this is the proportion of data to the left of that z-score. So the 68, that z-score in this proportion, this, I'm about to shade in this direction, this is 0.9306. All of that white space up into that border right there. 0.9868 is everything 0.9306 is plus the shaded area. So what you're going to do is take the big area minus the small area, and you get what's left over, the shaded area. So 0.9868 minus 0.9306, and what you get is 0.0562, or 5.62%. So the probability of this interval happening is 5.62% in terms of the chances. If I were to ask for greater than 70, that would still be another range. You would just do 1 minus the given number in the table A, because remember, if you look at table A, the diagrams, always to the left of the z-score, the proportion is. Let's do an example with a normal distribution again, in a continuous random variable. The normal distribution with a mean of 6.8 and a standard deviation of 1.6 is a good description of the Iowa Test of Basic Skills, vocabulary scores of 7th grade students in Gary, Indiana. Call the score of a randomly chosen student X for short. Find the probability of X is greater than or equal to 9 and interpret the result. So when you're finding this, you need to turn 9 into a z-score. So 9 minus the mean, 6.8, divided by the standard deviation, 1.6. And when you do that, you get 1.38, which turns into a proportion of 0.9162. So to the left of 9, everything less than 9, the proportion of data, or probability is 0.9162. But be careful, it says the probability of x is greater than or equal to 9. That's going to be 1 minus 0.9162, which is also called the complement. So 8.38% chance. So interpreting the result, you could simply say the probability of randomly selecting a student that has a score larger than 9 or greater than a 9 is 8.3% chance. Another thing, with continuous random variables, single events, so like whether I include 9 or I don't include 9, the probability of getting a 9 is 0. So if I were to add this probability to this one, it won't change it. So whether it's greater than or equal to 9 or greater than 9, it's the same probability. So the only difference between these two is that from this one, you add that 9 event, we know that the 9 event is the probability is 0. So this plus 0 is 8.38%. So whether it's greater than or equal to or greater than, it's the same probability. And continuous random variables kind of violates the rules or the intuition that you kind of built with discrete random variables where you have those single events that are countable. Remember, continuous random variables, these events aren't countable. There's an infinite number of them. Therefore, you can't count them, which means you can't find a single event probability. Or sorry, you can find a single event probability. It just happens to be 0, just like it says here.